All right. There I am. So you guys will have 2 class presentations. I just wanted to mention that. They are like in the 5th week and the 10th week, I think. And so the first one is going to be on one of the innovations that you write about. And so we'll coordinate that after our nice Monday holiday. So again, Monday's a holiday. So Martin Luther King's birthday. And so do something wonderful and positive for the world, even if it's just sitting and meditating on love. So just send love to everyone in the world. Here, this page is just some ideas about molecules, because you're eventually going to pick a molecule and write about it. And we talked about this page at the end of class. The second page is about polymers. And once we have double bonds are really reactive. And the double bond, they started with ethylene, which is just the double bond. This might have been the first plastic. Lab 3, you're going to actually do a little lab with plastics. Normally we do it in lab. It was actually a really fun lab, a really nice fun bonding thing. So you're going to get to do a kitchen chemistry. I moved it to next week because I'm not going to be available this weekend. And that way if people had questions, I wanted to be available. So I will post the lab, so if you want to get it over with. Yeah, and the other question was the folder for next week, I will open, so if you want to get your study set over with and not worry about anything until next Wednesday at 6, you can even do that. And so they react them, and they just make these long chains, which are, they then call it polyethylene. And they did it with propylene, and so 3 carbon. And so you can see, so these were each a 3 carbon group, and that's how they hooked up together. And then they did PVC and all the different ones that we might be familiar with, and Teflon, polystyrene, so styrofoam and stuff. These comments here on my notes were just for people trying to find a molecule. We'll talk about more in a couple weeks, but if some people like to get started early, again, this is something that's due in the 10th week. I've had people do like Kevlar, caffeine, theobromine. There's all sorts of stuff. And I'm sure as we go through the term, you're going to get inspired. But this was just showing that some of the plastics and stuff were polymers of a simple, a really simple alkene. And the reason for that is because alkenes are extremely reactive. So this was the first question on your study set that you had tonight, and I didn't realize that until I started doing the study set tonight. But boiling point, we just talked about it. Which one has a higher boiling point, cis or trans? And why?
Trans do.
Because
there's more bent carbons.
Not quite.
The surface area.
Yeah, trans have a higher surface area. Why do they have a higher surface area, Kristen?
Because of their shape, because of the way that they are branched or bent.
Yeah, they stack up. They zigzag. So they just keep stacking up. And so because of that, they can also form clots. These guys are like a double whammy. So they have a double bond, but they can stack up. And so they are found not in good places in our body. All right, solubility. These are all hydrophobic because they are only carbons and hydrogens. The big thing is this last piece, and that's what we're going to talk about for the next hour, is that they're very reactive and, yeah, highly reactive. Triple bonds especially are extremely reactive. That's why I had a test tube guy. You guys hopefully draw a really fun picture or a cartoon or a poem on your worksheet. So the type of reaction they go through is called addition. So really what always is going to happen is you have the double or triple bond. It's going to go from unsaturated and it's always going to go to saturated. Vincent, can you mute yourself? Because there's getting background noise. Thank you. Thank you. So you're always going to end up at a single bond. Always. And most of these don't need any catalyst or help to do because they're that reactive. All right, there are different names for these. First one is hydrogenation, and hydrogen is there. It means we're adding hydrogen. So if we take 1-butene and add hydrogen with words, so on the, I think on the worksheet, it has you do it with words and with symbols. You're gonna just go to butane. So butene would look like this with the zigzags, and we add hydrogen. And basically, we're going to fill in where the double bond is. The double bond is not stable, and we go to butane. If you showed it with the carbons, you don't have to show it both ways. I just do because some people, it helps them to see the carbons. Is we have this empty space here. And so one of the things that I would often is draw what you had. Those are hydrogens, right? If we show the carbons. And so here and here is where I have to add something, and they would just be the hydrogens would get added. So you just go to saturation. So 3-methyl cyclohexene. The methyl, if we draw it, my double bond is 1,2, and so methyl's at number 3. I add hydrogen, and all that's going to happen is my double bond is gone. I've added hydrogens there. The methyl is still there, but with the name, what's going to happen with the name? The double bond's not there, so the methyl gets to be at number 1. But if it's a cycloalkane, and the only thing you have is one side group, is our name is just methyl cyclohexane. So we're going to saturation. That's the stablest thing. That's the fossil fuels. That's what all of us are going to. All right. Second reaction. So that's simple. Adding hydrogen. Quick comment about hydrogenation. It has to do with cis trans. Probably heard of partial hydrogenation. So hydrogenation means we're adding hydrogens. Partial hydrogenation means they're not adding enough hydrogens. So you don't get one molecule reacting. Remember Avogadro's number? So in a spoonful of water, you have 6.02 times 10 to the 23. So there's gazillions of these molecules, and they only add half a gazillion hydrogens. So only half of them can react. And so what happens is they all want to react. They all like, open up, I'm ready to react, but there's not enough hydrogens to go around. So it's like, you know, I'm giving out candy to everybody in the class, and everybody's like, me, and there wasn't enough. And so they opened up. When they close, some of them go back to cis, and some of them go to trans. And that's how they were able to trick them into making trans. Partial means they didn't add enough hydrogen. And so when the reaction's over, they always open up, and then they didn't get extra hydrogens. And then they separate them based on boiling point, because they do have a different boiling point. And we got trans fats. The trans were able to stack, and so they're solid. And that's how they made margarine. And they thought it was wonderful because they said saturated fats. So when they started doing heart surgeries in the 70s and 80s, and they would pull out these big, long white gobs that were clotting up people's arteries, and then they would analyze them, and they were always saturated fats because saturated fats stacked up. And so they said, hey, let's not use pig fat, right? Suet and lard and stuff. We're going to switch to margarine because we can make it stack up. We can make it a solid thing. So Americans needed something to put on their toast. And what happened was they actually killed people faster. So margarine was actually developed during World War II because they didn't want to use butter because the cows were eating the food that was needed to feed the people. whole nother story. And so somebody figured out how to make margarine from corn. And they're like, look, we have a spread. And then the pig farmers' pigs started dying. And the pig farmers said, we don't want the scraps from your table. And so the pig farmers actually banned margarine like decades and decades back in the 70s. It wasn't until like 2000 that like the first bans on trans fats. They're not actually banned. They're like not wanted in our food. But in animal food, they're banned. So think about that. All right, halogens are the seventh family in the periodic table. So this is going to typically be chlorine that we're adding Cl2 or Br2. So you see those there. And it's just the same idea. So butene, we draw our butene and we add Cl2. Draw your arrow. So where the double bond was is where the chlorines have to go. So I'm just going to put stars there to help you see. The double bond is gone. You now have a star on each side and something has to go on the stars. They each get one chlorine. So we end up with a 1,2-dichloro butane. So something on each side, the double bond is gone. That's the key. And you add something to each side. Some students like the stars. You can put the stars as your new bonds. All right, the next one, Cis2 Pentene is going to look like this. And we add Br2. And it's now going to be a zigzag. My double bond was here at 2 to 3. That's where my bromines are going to go, is at 2 and 3. Again, you can draw carbons. I've noticed that most of you are doing zigzags, but please just always ask if you want me to redraw it with the carbons. So 2,3-dibromo. So chlorines and bromines, when they're added, it's just one at each position, and pentane. Any questions? All right. Hydrohalogen means we're going to add like HCl, a hydrogen, and a halogen. So we can always add two things, one on each side of the double bond, or HBr. And actually, we're going to go back one step. Adding bromine is how to distinguish in the lab that you have unsaturation. If we were in lab, you guys would get to do, again, Chem 105 had these beautiful, awesome labs that you would add bromine. Bromine is orange in color. So you're adding drops of an extremely toxic, nauseous thing that is orange. And it's how to distinguish unsaturation, which means that you have a double bond. And so what happens is this is orange, and you add it, and the color immediately is gone because this reacts in a femtosecond, 10 to negative 15th of a second. If it was saturated and you add the bromine, it turns orange. So if you add orange and it stays orange, it did not have a double bond. Double bonds are that reactive. Again, it's like the most reactive thing out there. Same with the triple bond. All right. So hydrohalogenation. The rule changes a little bit here. So we go to our 1-butene, and we're going to add our HCl. This guy's here because he became famous for this step. So here's where my double bond was at 1 to 2. So the question is, I'm not at the board, so the question is, does the hydrogen go at 1 and the chlorine at 2? Or do we put the chlorine at 1 and the hydrogen at 2? Or does it not matter? Because when we did this with alkanes, it didn't matter. It does matter with these. Dr. Markovnikov figured it out what it was. He had this awesome thinking cap, and he figured out what to do. And it is the chlorine, the thing that's not the hydrogen goes towards the middle. the hydrogen always goes towards the outside. Right. There's another way to think of it too. So here we have, and I'll show you as we're drawing these. So 1-methyl cyclohexene just means the methyl was there at the double bond, and we're going to add HBr. So the first trick is.
Would you move your paper up a little?
Yep. Well, there's nothing there. This is just previous stuff. Hopefully, that was last time's. Still the same thing. Double bond is gone. That's the key. And put a star where the double bond was for each side. And you have to add something to each side. The way the Markovnikov's rule is taught is usually the rich get richer. That's how somebody taught me, and I kind of didn't make sense, but I keep perpetuating it, right? Where it's more crowded, you keep adding stuff. It's kind of like human nature. Things go where things are crowded. So the bromine is going to go here, not on the methyl. That's a methyl. That's a CH3. And here, this is going to be the hydrogen. So it just keeps, we get overcrowding is what it is. So if there's something there, we keep adding something there. They like to go like to the same place. And let's do our names. On this last, well, this one, we just get 2-chlorobutane. I didn't show the hydrogen here. You can write it in if that helps you. You don't have to write the hydrogen in. I wanted to point out when you add 2 chlorines, you're going to have 2 chlorines in your answer. If you add a hydrogen and a chlorine, your answer has only 1 chlorine. All right, and then on this one, we would say 1 bromo, 1 methyl, because B comes before M and L. They have to each give a number because there is more than one side group, even though they're both at the same place. So 1 bromo, 1 methyl, cyclohexane. Yeah, and thank you. I keep this desk, I keep going off screen for some reason. Questions with this page? Oh, you know, the other thing I was going to mention about your celebration, that's in 2 weeks, so don't worry about it. Yeah, it is open note. There's no way I can control that. So just, you know, go back and redo your notes. Yeah, you guys have a huge advantage since it's all videotaped and our lectures aren't that long. All right, I'm going to go to the next page if there's no questions. And sorry, I'm looking for something. I think we're doing hydration next. So hydration, the key with hydration is the same as what we just did, is don't think of it as H2O, think of it as HOH. Water is not 2 H's and an O, it's an H and an OH. And so when we do the butene and we add the water, we get butane. We put our star on each side, and the OH is going to be just like Markovnikov's rule. The hydrogen goes towards the outside, the OH is going to go towards the middle. Now, this one brings up a catalyst. So here we go, a chance for a bonus question. What is a catalyst? We learned about them in Chem 104.
Reaction.
Sorry, somebody said something.
Does it speed up a chemical reaction?
Who's talking? Ezra?
Yeah.
It is something that speeds up a chemical reaction. And actually, it's a huge understatement when we say that. It makes it happen like it's billions, trillions fold speeding up. So you will often see the catalyst written on the arrow. So it just means sometimes we'll put it in parentheses. It's not reacting, so it itself is not involved in the reaction, but it's there to help the reaction happen. And Yeah, you guys must be having still issues with all the power because this is like a record number of people being kicked out by their Wi-Fi. So there's probably lots of issues going on. I'm oblivious to the weather that you guys are having and the mudslides and stuff. So, which is good. That means I'm not going to lose my Wi-Fi. The weather here is gorgeous. So let's name it. OH is hydroxy. So this is at number 2. So 2. Oh, I'm sorry. We're not going to say it's not hydroxy. This is an alcohol. So it is 1, 2, 3, 4. So it's butane. We drop the E and we put an OL to say it's an alcohol. So it's 2-butanol. So pretty simple. It's a segue into what we will be doing in 2-3 weeks, which is getting into the alcohol groups. All right. So Trans-2 Pentene, the double bond is 2 to 3. At number 4 has the methyl, and we're adding H2O. And again, the catalyst we would show on the line. And you redraw what you just drew without the double bond. That's the big key with this. The double bond's gone. We're going to do a triple bond in a moment. Put a star where the double bonds were. And now we have to put something on each side of the double bond. So one of these positions gets the H and one of them gets the OH. So which side gets the OH?
The right side, because it's the more crowded side.
It's towards the middle, yeah. It's toward the crowding, which is the methyl. So kind of like the methyl is pulling it towards it. So the OH is going to go there. When you show the OH, you always write the H that is attached to the O. You can leave the other H off, or you can show it. That's like a preference. I left it off on that one. I'll show it here. Some people, it's a visual thing, and so some of you have to see that I'm adding something on each side. Again, the stars is just something that has really helped a lot of students. You don't have to put the stars, but you absolutely can. And so naming. The OH ends up smack in the middle. So for naming, it takes preference. But since it's in the middle, the side group gets the preference. So the methyl ends up at number 2 now when we do the name. So 2-methyl. And then it is 3. So like double bonds, the OH has to get a number. So pentane and then OL. So the 3 is telling me the OL is telling me that's the OH group that is added there. It's the alcohol group. Questions? A quick comment. I'm going to go back a page to add something. I'm fascinated because the flow of my thoughts sometimes are very different writing on this than the board. For those of you who had Chem 104 last term, something that can help with this is the addition reaction is like a combination, meaning there's one product. Everything ends up together, which is different from the ones we did with the alkanes. The alkanes, it was a replacement. So a hydrogen switched places with something, and that's because it's saturated. So yeah. All right. And all right, so alkyne means a triple bond. So this is good practice for drawing our alkyne. That would be how you would draw. So a lot of people are asking me with the sticks. This would be 1, 2, 3, 4. And this blank is that we're going to have to add 2 HCl's because we have a triple bond. So we're going to add 2 HCl's. Every extra bond gets something added. So you do your arrow. We don't need a catalyst. If a halogen is involved, whether it's a Cl2 or an HCl, it's highly reactive. You don't need a catalyst. So we go all the way down completely to saturation. And you're going to put stars all around. 1 to 2, because for the first bond, for the second one. And you add an H and a Cl. Cl goes in the middle. And then you add another H and a Cl. And this is why that rule, the rich get richer, goes for these guys, the alkynes, is the chlorine keeps going to the same position towards the more crowded, towards the middle. It's like the monkey in the middle. It likes to be in the middle. It's like a child. Children like to be in the middle. We as adults like our space. We're like, no, I want the outside seat on the airplane. But these guys want to be in the middle. All right, so to name it, this is how we get them on the same position. So 2,2 dichloro. Well, I guess, Allie, I just realized, because you're not in Gresham either, so you're oblivious to that Gresham apparently is not Gresham, but yeah, that there's a huge power outages going on. So 2,2 dichloro butane. All right. So again, you can either write the 2 here, or sometimes what you'll see me write is just excess. If I write excess, it just means just keep adding as long as you can until you get to saturation. So don't let that word confuse you. It just means keep adding. So we can draw it. And again, if you don't like the zigzags, you can do it as zigzags like I did up there. What's going to happen is we're going to get chlorine, 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 chlorine. I'm going to draw this one with carbons because there's probably somebody who likes drawing the carbons. So at the triple bond, carbon number 2 has no hydrogens, but carbon number 1, there's a hydrogen there. And then we just keep adding HCl. So if you want, you can put the 2 in front of the HCl, or you can just know that it keeps adding. And you still have 4 carbons. The hydrogens, those are original hydrogens, and I'm sorry, Cl2. So we're going to keep adding Cl2s, and we're going to put them all these positions that no longer the double, the triple bond's completely gone, and everybody gets a chlorine. So we get 1, 1, 2, 2, and this is tetra. So when there's 4, somebody asked me this in office hours earlier. When there's 4, it's tetra, chloro, and then butane. I write the words because there's actually often several students where the words actually make more sense than the drawings. Some people, the drawings make more sense. Some people, the sticks. Some people, the carbons. So I'm trying to show different ways. Before we play this new game, is there any questions? I have to go back 1 page because I left something out. And it's amusing me because this is the first time I've done Chem 105, and it's like totally different to my brain looking on a piece of paper as opposed to on the board. It has to do with the hydrogenation one. The hydrogenation one also has a catalyst. So halogens, if you remember back from Chem 105, the halogens were right here next to the noble gases. Halogens are highly reactive. You could do, the reactions could be fluorine, chlorine, bromine, or iodine. They're almost, most of the ones we'll see will be with chlorine or bromine, but we could see fluorine or iodine also. Don't let that freak you out if you see it. They're so reactive, they don't need a catalyst. They're so reactive, and the double or triple bond is so reactive, no catalyst is needed. But water or hydrogen, you need a catalyst. And so the catalyst, when it's hydrogenation, is either platinum or palladium or nickel. They're actually in the same family here. This family is called the noble metals. They actually are not reactive. They're actually more valuable. They're the most valuable things on there. and I can't believe people wear it as jewelry because they're so extremely valuable, but to chemistry and to reactions and stuff. But if you see, we should have put them on the lines here. So you can pick whichever one you want. And again, if you see something on the line, that's just saying it's a catalyst. And sometimes people will put them in a bracket or in a parentheses to say, hey, it's catalyzing. That's not a big deal to me. But platinum, again, platinum, palladium, or nickel. That's why your catalytic converter, the platinum that is in there is a catalyst for that reaction. It's not this reaction, but the platinum is really good at a catalyst. Catalyst, again, is making the reaction happen, but itself is not changed by the reaction. All right, so last thing we have, unless there's another page that I'm not aware of. Oh, 2 questions. Okay, there are 2 new games that we're going to play. So the first game is you have 2 test tubes in front of you. So this is, we're pretending like we're in lab. We can all do a meditation now. Close your eyes and imagine you're in this beautiful, clean lab room, and the mice are running around doing the experiments. Anyway, in one test tube, if you want, you can draw a test tube. In one test tube, you have cyclohexane. And in the other test tube, you have cyclohexene. And at some point, I will do this demo and actually film it for you. It's quite impressive. And so it wants to know how you could tell it apart. Now, I'm going to tell you the wrong answer. What I will have students write is, well, the one that has the cyclohexene has a double bond. So they're in a test tube. You cannot see the hexagons. They're just going to look like liquids. Like when you look at a glass of water, do you see the H2Os? I mean, maybe some of you do. In meditation, I see the H2Os also, the hydrogens and the OHs and the hydrogen bonds and stuff. But you look at it and it looks like a liquid. So you're looking in here and all you see is a liquid. So how can you tell them apart? You do a chemical reaction. So somebody who hasn't gotten a bonus point this week, anybody know? I already gave you the answer for this. What would you do and what would you see to know which one's which? So what would you add? You're going to add something.
You're gonna add water.
Nope, not water. Because water, one of them reacts, but it's still going to look the same. Nothing, like you're not going to, you have to visually see something with our eyes. Not gnome eyes. Gnomes would see the water one. But there was something that I mentioned.
Don't you have to add a catalyst? Like we talked about the bromine and how the
Actually-
bromine changes color.
So yes, so I don't know who's talking.
That Melanie.
Melanie, thank you. So you're adding bromine. The only thing I'm going to correct you on is it's not a catalyst. It's actually a reactant in this case. So the bromine is a halogen, and the halogens don't need, they're so reactive. In fact, for the field you're in, whenever you're working with something that has a halogen, a bromine or a chlorine or a fluorine, you're acting extra precautious because they are so reactive. You're adding bromine, and you are right. I don't have an orange pen, so I apologize. So pretend like this is orange. So you add bromine, which is orange in color, and so Melanie, do you remember what happens? One of them is going to turn clear. Which one turns clear?
I don't remember which one turns clear. I can
Anybody
guess,
want to help
but
her?
I don't remember.
Oh, go ahead. Go ahead. Take a guess.
I'm gonna guess that the
The one that reacts.
hexene- Yeah, the hexene, right? The one
Yes,
with the double
there you
bond.
go.
Okay.
The one that reacts turns clear. So the unsaturated, the one with the double bond, the cyclohexene, is going to turn clear immediately. I mean, you add it and it's clear. It's like the orange was never there. And the other one, we can go with pink. The cyclohexane is going to be orange because it doesn't react. Now, if we leave it there for a couple days, it turns clear. It does react. I talked about it briefly on study set 2. And when we do the review for the first celebration, we'll run into this again, and I'll go through it more clearly when we do it then. Actually, next Wednesday, we'll run into it with the aromatics, and so I'll talk about it. But the double and triple bond, it is a clear way for chemists to know I have unsaturation. And clear meaning it in both ways. It does turn clear, and it means, bingo, I have an unsaturated compound. If it stays orange, it doesn't mean it's an alkane. It could be an alcohol. It could be, there's many different things it could be. But it just means you don't have that carbon-carbon double bond. All right, so that is what it means. So I'm not asking when I'm asking you to tell me what test you would do for unsaturation, that's what it is. And really, that's all we have for this first celebration, these first 4 weeks, because that's the special thing in hydrocarbons. So the other new game is that I give you the product, and you're going to tell me the reactant. So 2-2. So somebody different. It has to be somebody. Again, you can only get 1 bonus point in the week during these class. So these are people I have who've gotten a bonus point. So Caitlin, Melanie, Bianca, Vincent, Ezra, Jeremy, and Philip. So all the guys got a bonus point on Monday. All the guys. So none of the guys can answer this. And Caitlin, Melanie, you got one today, so you can't answer it. But somebody else, you can look back up for your notes and answer. We're trying to make 2,2-dichlorobutane. My question is, what do we start with, and what do we react it with to end up with this? It's like staring at us on the page. Anybody? Is anybody there? Vincent wants to answer.
I answered earlier, but I can answer again if you want.
Go ahead, Kristen. Does anybody else want to? Kristen's right. She did get a bonus point. I have to write her name down too. Did anybody else want a bonus point before?
Would you add the 1-butene to the hydrogen
It's
chlorine?
this reaction here. So it's the 1-butene plus HCl. So hydrochloric acid or muriatic acid. So 1-butene plus the HCl. It's this reaction up here.
It's not open, right? Windows are not.
So to get 2,2, to get them at the same carbon, So at 2,2, both at the same one, start with a triple bond. All right, so that was Emma. So somebody else wants to try the next one. You'll have to flip back a page to find the answer. And if not, I told Vincent he has to count.
Is
Like,
it the
I have
one?
a quick
oh,
question.
go ahead. I don't know who's answering because
This is Melanie. I have a question. Is
Go
it
ahead.
2 HCl?
Yeah,
Or is it-
so thank you for asking that. I
Okay,
want to
just wanna-
clarify that. So she is right. It is 2 HCl.
Okay.
And for you, especially with Javed, I don't know how he teaches this. He's actually is an organic chemist, but organic chemists usually don't worry so much about balancing the equation because, again, we're dealing with, in 1 teaspoon, even in a few drops, we're dealing with a godzillion number of these molecules. And so you're going to get reactions happening. But you are right. And so her question's excellent. A lot of students, they're like, I really want it to be a balanced equation. My teacher last term kept telling us it had to be balanced. So to be truly balanced, you would show the 2 HCl there, but we often leave it off or just say the word excess, but it is going to react. Yeah, so great question. And then somebody else was talking, and I don't know, for some reason it doesn't show me who's talking.
It's me, Sammy.
Okay, go ahead,
gonna
Sammy.
Do the next one.
Thank you. Go for it.
It's 1-butene plus Cl2.
Yes. So and this one, it is balanced how it is. Both of these are halogens, so you don't need a catalyst. If you need a catalyst, so if we were trying to make an alcohol to get full credit, you would have to show the catalyst. But to get them next door to each other, so if they're next door neighbors, so next to each other, I don't know, you can word it however you want. you start with a double bond. And we add, they say X2, which means Cl2, Br2. On this one, you would add HX, so you're adding a hydrogen and X. So yeah, so Emma and Sammy got those. Cool. I love giving bonus points. I think that's all I got. Is there another page? I have, my next page is actually our notes for next Wednesday. So all to tell you is Monday's a holiday. Your lab is due by Monday, but if you want the whole week off, just do your lab. You pick 2 things to do. So your next, and I will stay around for a little bit if you want to check your worksheet, and there'll be notes. Open the next folder, and I'll see you all Wednesday. So thank you. And